Hey everyone, so today we're going to be starting Unit 6. Unit 6 focuses very much primarily on right triangles. So the first topic that we want to talk about before we get into the right triangles themselves is the geometric mean. So the geometric mean between two numbers is going to be the positive square root of the product. Okay, so what that means, if we're looking at this example, the geometric mean x is going to equal the square root of two numbers multiplied together, a times b, or the product. Okay, so in our first example, if we have a being 9 and b being 4, the geometric mean would be 6 because the square root of 9 times 4 is actually the square root of 36. And if you know about perfect squares, we know that the square root of 36 is 6. Okay? So before we start working on more examples, I want to talk about perfect squares real quick. So if you're familiar with perfect squares, then this should be just a quick little review for you. If you've heard of them but you're not really sure, this is a chance to kind of figure out what a perfect square is. So anytime you have an integer that is squared, okay, so 3, 4, 5 squared, it's going to create this new number, right? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, and 25. What I mean by perfect squares, that's going to talk about this right side right here. So all of these numbers here, 1, 4, 9, 16, 25, these integers or whole numbers are known as perfect squares because if we take the square root, okay, so the square root of 9, we can say that it's 3 because here 3 times 3 is 9. So a perfect square is whenever you have a number that when you take the square root, the answer is a whole number or integer. Okay, so anytime there's a decimal, you will not have a perfect square. Okay, so perfect squares are always going to be integers, whole numbers. Okay, so thinking about that, we're going to start working on an example. So find the geometric mean between 8 and 10. All right, I know that my geometric mean is the square root of the product, so square root of my two numbers multiplied together. For the purpose of working with these geometric means and right triangles, we want to simplify our radical as much as we can. Okay, we're not just going to plug it in a calculator and get a decimal. We are going to actually simplify these down to the most simple form. Okay, so in order to do that, we want to think about perfect squares and factors. Okay, so I'm going to say that the square root of 8 times 10 is the factors of 8, 2 times 4, times the factors of 10, 2 times 5. Okay, so the reason I'm doing this is I want to look for these perfect squares so that I can pull them out of my radical. Okay, so I notice here I have 4, which is a perfect square, and then I also have 2 and 2. Okay, so if I multiply together 4, 2, and 2, I actually get 16. Okay, this is known as your associative property, so we're just basically regrouping these. Okay, so what I'm going to do, square root of, now I'm going to have 16 times 5. Because again, I want to find as many perfect squares as I can to make my life easier during this simplification process. Okay, so 2 times 4 times 2 is 16, which is a perfect square. Once you're here, and we have it simplified as much as we can this way, we're going to take these perfect squares, so here we have 16, take them out of our radical, okay, so the square root of 16 is 4, and then now we just need to rewrite the radical in what's left. Okay, the square root of 5 is not a whole number, so we're just going to leave that underneath our radical. Okay, so x, or our geometric mean, is going to be 4 square root of 5. This is our most simple form of our answer. Okay, so continuing on with another set of examples, okay, finding our geometric means, find the square root of our product, so 5 times 45. If you can multiply these together and automatically notice the perfect squares, cool. If not, factor it out. So we get 5 times 9. Okay, so I'm just breaking down those factors. I have two 5s, okay? Anytime you have a pair of numbers underneath your radical, those create a perfect square. So we're going to take one of these out, but then we also have 9, which is a perfect square, okay? So all I have to do, these arrows are going to represent my numbers I'm quote-unquote taking out. So we have 5 times 3. Again, I'm taking the square root, so square root of 5 times 5 is the square root of 25. That becomes 5. The square root of 9 is 3. So here, now we are going to have our geometric mean equaling 5 times 3, or 15. Okay, and then one more example. The geometric mean of 12 and 15. We're going to take the square root of their product. Okay, so here we're going to have the square root of 3 times 4 and 3 times 5. Again, we are focusing on the factors that we can get some perfect squares out of, okay, if possible. So here we have 4, and then we have a pair of 3s, which would make a total of 9, which is a perfect square. So taking out our perfect squares, we're going to have 3 times 2, and then we're just going to be left with this square root of 5, because that cannot simplify down anymore, unless it's a decimal, but we don't want decimals. Okay, so here x is going to equal 6 times the square root of 5. So let's put a little pin in the geometric mean, and let's talk a little bit more about right triangles. Okay, so anytime you have an altitude drawn to the hypotenuse of your right triangle, there are going to be two other triangles that are formed that are similar to the original. Okay, so in this example, we have ACB, our big triangle. We have this altitude that's drawn, okay, which is actually creating two other triangles, okay, that are similar. So if you keep in mind that an altitude within your right triangle, as long as it goes from to your hypotenuse, then you're going to have 3 total similar triangles. So let's look at an example of that. Okay, for here we want to write a similarity statement identifying the 3 similar right triangles in this figure. Okay, so what we're going to do, I'm going to take my triangles, basically break them apart, reorganize them, line them up, and write my similarity statement. So I want to start with my main original triangle. Okay, so that's going to be FGH. Okay, so let's just redo this one. This is my original. Okay, and then as I'm going through and rearranging these new triangles, I want to focus on lining up my right angles. Okay, that way I know my triangles are similar or in the same kind of position. Okay, so if we start looking at our altitude, okay, I see that I have a right angle here down at J. So I'm going to say G to J is my altitude, and then J over to H, this direction, okay, is going to create this long leg. Okay, so J again was my right angle, and then H back up to G is my hypotenuse. So we have 2 right angles in the same position, and our hypotenuse is in the same position as well. Okay? So looking at our last one, we have G to J again, so G to J. Okay, our right angle is at J. As we go the opposite way, we have F, and then back up our hypotenuse up to G. Okay, so this one, JF, is actually our short leg, but the important thing is that we have our right angles in the same position, and then these two have this shared altitude side, GJ. Okay, so as we're writing our similarity statement, we're going to look at each triangle and say, okay, I need to go in the same exact order. So if I go F, G, J, okay, so top, right angle, and then bottom right, then I know that that's similar to G, J, H, which is also similar to my last small triangle, G, J, F. Okay? So that's how we write the similarity statement of a right triangle, okay, when we have that altitude dividing them. So now we're going to take those two topics that we just covered, geometric mean and the similar right triangles, and marry the two concepts together, okay, and see how we can find missing values. Okay, so we have these two geometric mean theorems that relate to triangles, right triangles specifically. So the first one is in relation to the altitude. So the geometric mean altitude theorem is talking about the altitude. So when it's drawn to the hypotenuse, it's going to separate your hypotenuse into two segments. Okay, so the length of your altitude is going to be the geometric mean between the specific lengths of these two individual segments. Okay, so h, or my altitude, is equal to the geometric mean of x and y, right, or the square root of x times y. Okay, so another way that you might remember this, okay, you can think of your altitude equaling the square root of, and this is going to be in relation to your hypotenuse. So part of your hypotenuse times the other part of your hypotenuse. Okay, so your altitude, again, separates your hypotenuse into two segments. So the length of this altitude is the geometric mean of those two segments. So part times part. So let's look at an example of finding the altitude. Okay, so here in this example, we have to find x, y, and z. The first problem that we're going to work on is x, or our altitude. Okay, so I just learned that x equals your altitude, okay, so your altitude is x. That's going to equal the two segments of your hypotenuse, so part times part, okay. So one part is 5, and the other part is 20, okay. So, like we did at the beginning of the notes, we're going to take the geometric mean, or simplify this radical down to the most simple form, okay. So if you need to factor these values out, you can, okay. I know this is actually the square root of 100, all right, or if I'm not sure of how those factors work, I can say 5 times my factors of 20, which are 4 and 5, okay. Pick out your perfect squares. So we have 4, which becomes 2, because the square root of 4 is 2. And then we have a pair of 5s, which would be 25, and the square root of 25 is 5. Okay, so our answer here, x, would be a value of 10. Okay, or if we recognize that 5 times 20 is 100, the square root of 100 is actually 10, because 100 is a perfect square. Okay, either method works. If you need to factor it out to see your perfect squares, fine. If you can see that it's already a perfect square, that works as well. The thing to remember, altitude equals part of your hypotenuse times part of your hypotenuse. Okay, and then moving on to the last theorem that we're going to talk about today, the geometric mean leg theorem. So this is talking about the legs of your right triangle. So your legs would be either B or A. Okay, again, your altitude divides that hypotenuse into separate segments. Okay, and then we are told that the length of the leg of the triangle is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So let's break that down a little bit. We have B, which is a leg. Okay, that's going to be the geometric mean of the segment that's adjacent times the entire hypotenuse. Okay, so if we were to write that down, B, our leg, would equal part times whole, okay? Or in this case, x times c, okay? And for our other leg, we would have A, this green one. Again, it's a leg, so we know that it will equal the part that's adjacent times the whole hypotenuse, c, okay? So this would be, if we wrote it as letters or variables, x times c. So let's look at that in our other triangle, okay? So we have x, y, and z. We just solved for x. That was our altitude. Now let's look at y, okay, because that comes next in the alphabet. All right, so y equals, we notice that y is a leg, so it's going to equal the part that's adjacent times the whole hypotenuse, okay? So the length of our whole hypotenuse here is going to be 25. So then let's just plug in our values. The square root of 5, because again, 5 is adjacent to y, times 25, all right? 25 is a perfect square, so if you know how to take that out and simplify, awesome. If not, let's factor it down. 5 times 25, which is 5 times 5, okay? Again, 25 was a perfect square, like we just mentioned. Okay, well, my pen's not working. There we go. Okay, so 5 and then 5 and 5. So now when we simplify down y, let's pull this up here. Y equals that 5, which this perfect square of 25 comes out, and then we're just left with the radical 5 because that can't simplify anymore. Okay, so all I did, 25, the square root of 25 is 5. And then the square root of 5 right here, I couldn't reduce that, so that stays as is. Okay? And then our last leg is z. Again, leg equals part times whole. Okay? So the part that's adjacent to z is 20. So we're going to have 20 times 25. Again, you can multiply this out and figure out your perfect squares that way, or start factoring early on. So we have 4 times 5, and then again, we can leave this as 25 because 25 is a perfect square. Remember, we just did this earlier. So now we're going to have our perfect square of 25. So that becomes 5 times our perfect square of 4, which is 2, because square root of 4 is 2. And then the other 5 that's left has to stay. Okay, so z will equal 5 times 2, which is 10, square root of 5. Okay, so this 25, square root of 25 is 5, square root of 4 is 2, 5 times 2 is 10. So all of that comes outside, and then we're just left with the 5 underneath. And that's what we're doing today, just working on these examples, okay? Be sure to practice on the corresponding assignment, and let me know if you have any questions.